This is my interview with Jerry Chow from IBM. He is an IBM fellow and director of quantum systems at IBM, quantum computing, and he knows a ton about quantum computing, something that I've been learning more about lately. So in this interview, we talk about everything from obviously the basics of quantum computing, the difficulties, where we are in the timeline, how it might affect artificial intelligence, and does encryption break when we bring quantum to production. We covered so many cool topics. Check it out. Here it is. All right, Jerry, thank you so much for joining us today. Really excited to be talking to you. I am an absolute newbie when it comes to quantum, and I remember seeing your talk at the IBM analyst event late last year, and you were just able to explain quantum in such simple terms that I understood it, which was wonderful. So really excited that you're here and able to chat with me today.
Great, glad to be here, and thanks for those kind words about that presentation from before.
Yeah, I mean, quantum, to say the very least, is an advanced subject. I think some people kind of understand what it is. I kind of had like a very high level understanding of what it is, but maybe you can break it down in the most simple terms. What is quantum computing, and where are we, like, kind of what is the state of quantum computing right now?
Yeah, I think it's certainly a very exciting field, and an exciting field to work in. But also, I think it runs into this thing of like people really want to know the heart of like what is quantum computing and how it works. That we almost sometimes forget. We don't ask all those questions of how does our regular computers work, right? We often just take for granted how our computers work.
Yeah.
But in the end, like what we're trying to build with quantum computing is it's really a different form of computation, right? Like, so for the longest time, we've computed based off of data representations, right, that are represented by information carriers like bits, zeros and ones, binary. It's how we know how to process information. It's how we've built an entire ecosystem of computational tools and everything so forth that has advanced our modern computation today. And there's the whole Moore's law and everything of progression over the many decades of technologies that have scaled our ability with computational ability with traditional bits. But quantum computing really completely changes the actual fundamental nature of how you can process information. And it's because the fundamental unit of information is no longer a bit, but it's these quantum bits. And they follow the rules of quantum mechanics. And here's where we can get into details of what that all means. But really what it just means is that the information follows different sets of rules. And the mathematics for how the information is processed is different, so that we have the opportunity to actually address certain types of problems, problem instances, in a much more efficient way, and in some cases even exponentially better than you would do with a traditional bit-based computer, right? And so that's really sort of the differentiating capability, is that there's a very much a different underlying mathematical structure to how information is processed and how data is represented. And so we have the opportunity for this advantage using quantum computing for certain tasks.
Now, that's a really good explanation. And you mentioned there's some use cases that it really exponentially exceeds what we're able to do with traditional computing. I've heard some instances where a traditional computer would take billions of years to compute something, where a quantum computer will take minutes, which is kind of insane to think about. So correct me if I'm wrong on that. And then maybe just mention a couple examples of those use cases where quantum really excels.
Yeah. No, I mean, that's certainly the type of gap that we're talking about, right? Like, we're talking about problems that you would never be able to solve with classical traditional computers, that now we open the door to possibly solving using quantum computers. So really, that's the idea. So when you talk about something that, if you had the largest supercomputer in the world, might take some unknown amount of time, we do try to hopefully have the right structural problem there that we can solve on a quantum computer in much shorter time. And problems like this of ones that we can address, right? Or that I hope to address. Um, Probably the most famous one that was proposed with an algorithmic uh, um, exploration back in the mid 90s was actually factoring large numbers, right? And this is behind a lot of modern day encryption. The fact that we can multiply numbers very easily, but going into reverse is exponentially costly, right, for classical computers. And there happened to be a theoretical algorithm developed in the mid 90s called Shor's algorithm, which could do this in exponentially shorter amount of time using a quantum computer. But then other applications, studying molecular structure, understanding the core of natural materials in terms of how electrons interact with one another, right? So this is very much at the a heart of a lot of materials discovery and understanding interactions between various molecular structures. Very fundamental for things like drug discovery and things of that sort, right? And here again, we're dealing with a problem that exponentially blows up in terms of classical resources. When you have a very complex molecule or molecular structure, you end up having an exponentially large number of interactions between various electrons, and that becomes very hard to model. And there are ways of doing that using classical computers where you can approximate that, right? But it becomes also very costly in terms of using classical computing resources. And it just so happens that that's the exact type of, the way that those electrons are interacting with one another are quantum mechanical by their nature, right? And so we can mimic that, and we can actually map that onto qubits, right, which we have control over, in their interactions, which we have control over. And so really that's the power there, where we can use a different representation of this problem on a quantum computer and have the chance to solve it.
So you mentioned encryption, and I want to stick on that for a second. So encryption is really the underlying security layer of really all traditional computing. It is also what allows crypto assets and like Bitcoin, Ethereum, that is their fundamental principle of how they work. But if all of a sudden quantum computers can kind of reverse engineer and figure out how to break those encryptions, what does that actually mean? I know a lot of people say that's the end of crypto, the end of encryption. Is that true? Is that an overstatement? Or like, how do people think about this?
I think the way to think about that is it's not an all of a sudden thing, right? Like with the whole point of talking about it now is that we can kind of project for when that's happening, and we're building the technologies to get there. But the point is that there are quantum secure and quantum resistant cryptographic methods that exist, right? So there are different types of mathematical structures that you can build behind your cryptography, like lattice-based structures. There are a number of protocols that were basically supported by NIST, the National Institute of Standards, last year, right, as quantum safe protocols. They exist. The biggest issue with using them is just inertia, right? Getting an entire industry or industries, right, to move all their data and their their cryptographic exposure to a new standard and a new protocol. No one wants to do that themselves, right? It's obviously overhead and things of that sort. And so, you're starting to see industries starting to talk about this, from the telecom industry to banking, and they know that that day is coming, right? That quantum computers will be there that can break the encryption that they typically use. And it's just a matter of finding that right moment to start moving the data and adopting a lot of these quantum resistant, quantum safe protocols.
And you said it's not going to be an all-in-one thing, and it's kind of interesting to think about. There's not really going to be this solo actor who all of a sudden discovers how to do quantum computing at scale in their garage, right? It's just it's so sophisticated, so complicated, so costly. Could you envision that happening in the future? Or really, there are only very few companies right now who are working on quantum, IBM being one of them. So how should people think about that?
Yeah, that's right. I mean, you think about this from the point of view of that, we're building infrastructure that is at the level of, data center, supercomputer scale, uh, um, hardware, right? Plus the networking and infrastructure on top of that you need to make it a fully usable computing service, right? So it's not necessarily a garage thing. That'd be kind of fun if it was, but it's more of quite a capital intensive investment to build this, right? And it's not a single shot type of thing where it comes out of nowhere, right? But
Yeah.
we have stated roadmaps. We've, certainly at IBM shown both in our history of like what we can do year after year, and also prognosticating for the future of where we want to be year after year, right?
When I was a little kid and I first saw a motherboard for the first time, I was completely enamored by it. It really changed the trajectory of my life. I knew I wanted to be in tech. I don't know. There was something just about that green motherboard with you could see all the little transistors. And when I look at a picture of a quantum computer, I get that same feeling. It is just an incredible piece of machinery and extremely complicated. And I'm going to put a picture of it on the screen right now, or at least one version of it. Can you talk about the very high level components that go into making a quantum computer? I know cooling is a big
Mhm.
aspect, but
Yep.
maybe you could just talk about the major elements.
Yeah, absolutely. And I think uh, uh, it's we certainly are glad that the picture that people um, iconically have of quantum computer actually is based off of technology that we've been building at IBM, right? But to be kind of specific here, like we are using technology based off of superconducting qubits, and so there's semiconductors, right? Semiconductors we all know about, and the materials there that go into our processors and our CPUs and the GPUs today. But we leverage a different set of materials, superconductors like aluminum, niobium, titanium nitride. These are different types of superconducting materials that behave very funny when you cool them down. They superconduct, so they effectively have no resistance. Um, and when you start to build structures or circuits out of these materials, you can start to have them behave in interesting ways. And with the right type of circuit elements in these using these materials, we can build qubits that behave quantum mechanically, and we can string them together, and we can make basically a chip full of these qubits to act as a effectively, it'd be the core of a QPU, right? That you can leverage for quantum computing. Um, but the key thing for these superconducting qubits is they need to be cooled down for them to function properly. And for that matter, they need to be cooled down to roughly 10 to 15 millikelvin, right? So if we think about the degree scale, right, we know certainly that zero degrees is when water freezes. Um, so we can go to around and that's around 273 Kelvin if we go into the Kelvin scale. And then at 77 Kelvin, that's where we have liquid nitrogen. So we know about liquid nitrogen. People use it for some cocktail drink sometimes, or for making ice cream, right? So that's already pretty cold. Uh, if you go out to outer space, right, that's around 4 Kelvin. And we are now even several orders of magnitude colder than that, right? That we need to get these
That's
devices down to that
crazy.
level. Um, uh, Phenomenally, right? Like, what's really cool though is that it's not a hard technology to get that cold, and there exists refrigerators that let us do that just with the turn of with push of a button, right? And uh, it leverages a technology known as cryogenic dilution refrigerator technology. But by using various combinations of pumps and flow cycles of helium and helium isotopes, we can construct these refrigerators that lets us cool these devices all the way down to 15 millikelvin. And when you look at the picture of a quantum computer, right, that looks like, this golden chandelier and with these various different elements in
Yep.
it, you're actually looking at the interior of one of these cryogenic dilution refrigerators that itself cools down the chip that sits all the way at the bottom and gets it down to that temperature. Of course, there's a lot of things that you need besides the cooling. And in fact, the cryogenic infrastructure itself has multiple stages of cooling. So every plate that you see within there, it gets successively colder and colder. And normally, obviously, it doesn't function with it just completely open. When it's open, it's for us to look at, right? But normally, it's all closed up with various different heat shields, and every single layer is a different temperature. So it goes from room temperature to 50 Kelvin to 4 Kelvin to 800 millikelvin, 100 millikelvin, and then all the way down to 15 millikelvin. And that's where the processor sits. And the rest of the architecture cools down like wiring cables that goes to address the qubits, cools down other passive components that might condition the signals that we need to control the qubits, and then other components that amplify the signals coming off of the qubit processor, so that we can actually digitize and turn the signals off of this superconducting quantum processor into, classical data, zeros and ones that we can then do something with using traditional classical computers.
So wait, if I understand that correctly, you are you're taking the quantum computer and then at the very end converting it to binary. Did I understand? I don't
Absolutely.
think I understood that. Wow.
You need to think of that as like the quantum computer itself, right? In the end, you and I can only control things in the classical world. So we can only program with things that we still need to use classical computers to actually interface with this, right? So in many ways, the inputs are still classical. The outputs are still classical. It's just inside the machinery of the quantum computer. It goes through this different mathematical formalism for, leveraging quantum mechanics to process information in an entirely different way that greatly expands, right, the possibility of things that we can compute.
Yeah.
Right. But in the end, right, like the full quantum computer isn't just that, the refrigeration unit itself. It's also includes control electronics that are classical, as well as a classical computer that acts as a controller, or even a traditional compute cluster that pre and post processes the results that come off of the quantum computer in ways that then it becomes a cycle, right? You don't just run it once and you're done. You need to do a lot of things where you're handing things off between your classical and your quantum computer back and forth.
And you talked about the input and the output being binary or classical computing. What does the software layer of quantum look like? I mean, it seems like it would be incredibly complex. Is there standardized libraries? Talk a little bit about that.
Yeah, no, that's a great question. And I think, obviously, hardware without software is useless really in most ways. And in a lot of regards, when we first placed these systems on the cloud, right? It was in 2016. We put a simple 5-qubit machine out onto the cloud for users to access. And right then and there, we had to define how are we going to let people program this thing, because up until then, a lot of the experiments that we were doing we were doing them as physicists, as quantum physicists, as experimentalists, turning knobs and looking at dials, getting results, right? And it's not a real computational model, but we defined a simple graphical interface at that point, which was based off of an element called the quantum circuit, right? So the quantum circuit, you can think of it as the real unit of computation. If the qubit is the unit of information, the quantum circuit is the unit of computation, and it involves various gate operations on different qubits, and it involves measurements of those qubits to return classical results. Think of that really as the low level assembly language of a quantum computer, right? And so you're just like in a classical computer, we talk about building up circuits in the level of gates, like NAND gates or OR gates. We have that analogy there, right, with this level of quantum circuits for the quantum computer. But then we need to build abstraction levels on top of that to actually make it meaningful, just like you would in a classical computer, right? To actually turn it into, like you said, eventually libraries that are callable for various different applications. And so, then that next layer of that was 2017. We introduced Qiskit, or which is short for Quantum Information Software Development Kit, right? And Qiskit started to lay out like different APIs for access that we felt users needed to be able to tap into, right? That there's layers of dealing with how to map problems, or how to optimize the problems, or how to actually execute these quantum circuits on the actual physical hardware. And so we built out those different layers, and we started to grow the community in terms of learning how to program in Qiskit, right? Today, Qiskit is the most popular software toolkit out there, right? In terms of usage. But we're still in that mode of further defining those abstractions, right? And we have a much better idea now, though, that we don't need people all to know all the nitty-gritty details of how to operate these qubits or to talk assembly, right? Like when you're programming your computer, you don't program in the physical gate architecture, right?
Right.
You like you mentioned, you call libraries, you call functions, and so we're building out those abstraction layers today, and especially we're now seeing that quantum computing is best used within your full fleet of computational tools, right? That you need to use your traditional cloud endpoints, right? You need to use your traditional, and you're going to maybe call some GPU cluster as part of your computation, and so we need to be able to leverage these various different forms of compute, right, in an elastic fashion, right, for the different types of problems. And so we're building out all those abstraction layers, all these pieces that eventually leads towards, we just introduced this concept of Qiskit functions last year, which are more application driven, right? If your end problem is in chemistry, then there's a function for that. If your end problem is in optimization, there's a function for that. And those will map your problem onto quantum circuits and assembly and so forth, but you never have to necessarily know about that.
So I want to just double click into something you just talked about. You said developers are going to need to essentially tap the right type of compute for whatever their use case is. Now, one of the questions I meant to ask you is, should people think about quantum computing as the complete future of computing? Is it going to replace traditional computing completely? You kind of answered it, but maybe just touch a little bit more on that.
Yeah, no, you got it. I think that's a really good question, and maybe a common misconception, right? That it just replaces everything. And in fact, it doesn't, right? It's good for certain things. The language of qubits, or the language of quantum circuits, right, as a different data representation, are best to target, specific problems that map most efficiently onto quantum computers. There are other problems that map best towards tensor networks, and so therefore, leveraging GPU clusters, right? And then, of course, there are still those problems that map best to traditional qubit bits, right? And in terms of using your regular CPU architectures. We really see this, right? Like we at IBM, we sometimes call it bits, neurons, and qubits, right? Three various computational representations coming together as the future of computing, right? Because in the end, you're going to need them all. And in some sense, the tensors and the quantum circuits, they've just expanded the possibility of computation that you have at your fingertips.
And Jerry, do we know the universe of problems that can be solved by quantum computing, or are we still figuring that out right now?
There's another great question, and still figuring that out, right? I think a
Yeah.
big part here is that I mentioned earlier, we mentioned a couple of use cases, right? Like breaking encryption, understanding molecular structure. So there are some known algorithms. There are some known problems that on pen and paper people have mathematically proven. There's speed ups and gains to use a quantum computer, right? And they might require a certain size of a quantum computer and certain number of executions or size of the circuit. Um, uh, but what's fascinating is that there's so much in terms of what we don't know, and that is already beyond what you can simulate classically, these same types of quantum circuits, right? That there's just a whole untapped area of exploration and discovery for new algorithms to leverage this as a computational resource.
All right, that makes a lot of sense. And then kind of dovetailing off of that point, I'm extremely passionate about artificial intelligence. The vast majority of different videos, the newsletter, all of the content I produce is about AI. And I really don't understand the intersection between quantum and AI. And I would love to get your take on how people in the AI industry should think about quantum. Where is it? What can we expect in the future?
Yeah, no, it's a good thread to pull on, and there's the way I like to think of it is there's two parts of it, right? There's uh, AI for quantum, and then there's quantum for AI, right? And so on that first front, the AI for quantum, uh, that's relatively straightforward, right? The idea here that from the point of view of for example, a Qiskit code assistant, something that we introduced last year, right? That you can use models to help developers, right, program in Qiskit more effectively, more efficiently, you know, based off of previous trained Qiskit
Nice.
code, right? That's almost a simple self win, right? Um, um, AI models also, right, come into play though for certain kinds of optimization tasks, and from the point of view of mapping a particular circuit into its most optimal form to run on hardware. We introduced this tool last year called the uh, AI transpiler service, right? The Qiskit AI transpiler service, which does that type of mapping, and underlying is using various reinforcement learning principles to drive that kind of optimization, where it can actually perform better than some sort of out of the box transpilation or compilation type of schemes. And so that's another area that we certainly see it coming through, right? And I think on that front, using AI to help us optimize workflows, how best to break down problems, that is a lot of sort of untapped area for us to continue to explore, right? Uh, Now the quantum for AI side is a little more complex and I think nuanced to describe, right? Here, people have been talking about quantum machine learning for a long time, from the point
Mm.
of view that there are actually there have been at least some explorations of algorithms for doing certain machine learning tasks like classification, um, like learning that leverage quantum circuits. And here, there's still a lot of research going on in terms of finding exactly what that kind of advantage might look like. For one thing, there are an interesting thing here is that that encryption problem that we talked about earlier, you can actually frame that like a classification problem, where it's actually a structured data problem, where you're trying to find this inherent structure of the factors of this large prime factors of this large number. And it so happens to map very well to quantum circuits and map very poorly to traditional support vector machine learning models. Okay, so there's a whole exploration in that front of like finding where are there interesting data sets that have this underlying structure that lends itself well to using quantum computers to perform, some of these machine learning tasks more effectively. Um,
Okay, please continue.
yeah, and then so so finding new algorithms, right, that leverage quantum circuits in that type of machine learning slash AI space, completely ripe for development. And then the other thing that I think is really exciting and sort of, it's a it's out there for us to take and to explore, is as we are building these um, supercomputers, high performance computing of the future, where from our point of view, we call this quantum centric supercomputing, right? We're going to have GPUs, we're going to have CPUs, and we're going to have QPUs co-located. There's an opportunity for us to really find, right? And this is less maybe a statement about AI, but more a statement of finding the right types of problems to map onto these different endpoints. It might so happen that there are AI types of um, uh, uh, um, tasks that map very well to these different endpoints. Um, but it's almost like it's something that we need to build it to in order to explore it. And we're already trying to find those key partners to build this, future of computing infrastructure in order to tackle this head on.
Okay. Um, there have been a couple topical quantum things stories that have come out in the last few weeks that I wanted to get your thoughts on, if we could do that.
Yep.
A few weeks ago, Google published a paper with a project called Willow,
Mm-hmm.
and I read the headlines and I tried to understand a bit about it, but maybe you can explain what they were able to achieve in simple terms, and then what your take is on it, just from a kind of deep in the weeds
Yep.
researcher yourself.
Yeah, no, you got it. I mean, so their Willow device basically lets them study quantum error correction, right? And they were able to look at a particular quantum error correction code known as the surface code, and showed that it performs well in terms of effectively behaving as a logical memory. Now, let's take one step back, right?
Yeah, perfect.
Um,
Yeah.
uh, Biggest problem with building these quantum computers that we have today are fundamentally that they have errors. So, we talk about building superconducting qubits. They are little metallic structures built into substrates, right? And they're basically little electromagnetic antennas that we expect them to behave exquisitely, at an atomic scale to exhibit this kind of quantum mechanical phenomena. But guess what? These things are little antennas. They like to interact with other things that are in the environment, in how you fabricate the devices, how you package the devices, and how you control the devices and bring signal wires down to it. That all can lead to you losing your quantum information, right? So you have these qubits, and you have to program these qubits, and you need to operate these qubits with one another and entangle them and perform these gate operations at that assembly level. But if you lose your information after you do a number of those operations, then you have no computation, right? Um, so in the end, with any kind of qubit platform, we need to address these types of errors. And uh, there's various strategies for doing so in terms of, there's some more near-term strategies, which we also leverage, which are known as error suppression and error mitigation. Lets you try to understand the noise from at a fundamental level and remove the noise in certain ways in terms of running multiple circuits. This is how we do error mitigation. But then there's error correction, where fundamentally we're using concepts of error correction codes, which are common in classical information theory as well, right? So, just as an example, a very simple classical information code is something like just the repetition code. If you're afraid that your one bit will have an error, make a copy of it twice, have 3 bits, take a vote of those three,
Mm.
and pick the one that is majority, right? Take that result as the majority. Fun thing about uh, quantum bits is you can't just do that copying, and so you actually need to build more complex codes that lets you um, find out certain information about the qubits without losing the information carried by the qubits. And in the end, the idea of quantum error correction is that you need to build more physical qubits, right, into a network that lets you encode your uh, qubit information into that larger number of qubits. The service code, which is the one that Willow, right, has been testing, is a very popular quantum error correction code. The idea is you make a nearest neighbor lattice of qubits, and some of these qubits are what's called data carrying qubits, so they actually have the information that you want stored. Other qubits in that lattice are uh, uh, error error uh, error syndrome qubits, ones that you actually measure to find the errors that are occurring on the other qubits. The way that I think of it, like one way to think of error correction is you're playing some really large game of Minesweeper, right? Where you're trying to tag certain qubits, right? With this one is going to tell me that there's an error on these other ones, right? And based off of that, figure out like where I need to make corrections on the information carrying qubits. Um, Now, the service code was actually is it again one of the more popular codes was actually an idea that some of our error correction team at IBM had studied many years ago, and actually in the early 2010s to 2018 or so, we were leveraging the service code as well. But we've actually now moved on to different types of error correction codes, which are uh, let's see, how do you measure? Maybe let me just state that again, right? So, um, uh, the service code is a very popular code that people have been studying in order to make and explore error correction. But one of the fundamental limitations of it is it's very expensive in terms of the number of qubits that you need in order to actually encode logical qubit information. Sometimes you hear about people building a full-scale quantum computer requiring some millions or tens of millions or even hundreds of millions of qubits. Is because people are thinking about it from the point of view of needing to build error correction into these kind of surface code architectures.
Mhm.
At IBM, we've been studying actually how to build more scalable error correction codes. And last year, we actually introduced a different kind of error correction code called a low density parity check code. We won't go into the technical details here, but it reduces the overhead of the number of physical qubits you need for your logical qubits by an order of magnitude, right? So in order to actually build a reasonably scaled system, we're going to need only, say, 10,000 qubits or 100,000 qubits instead of several millions.
Okay, got it. There's a lot of very complex topics that you just covered. And I actually just want to ask you a quick aside on that.
Yes.
If somebody is absolutely fascinated in quantum, what is the best way to learn and just start the journey?
Yeah. Well, to learn, we actually have another plug for ourselves. We have a lot of learning
Please.
content on um,
Where
on
do they find
on
it?
on IBM Quantum, right? So, I mean, we have it ibm.com/quantum. There's a lot of learning resources there. Get you from, running your first quantum circuit on real quantum hardware to learning about the fundamentals of error correction and what it means to, program a quantum computer, right? All this is out there. We also have a series of videos from um, world-renowned expert John Watrous, right, who talks through many of these concepts. He was a former professor from Waterloo who goes into exquisite depth, right, talking about this type of stuff.
So I'll drop the links that you just mentioned in the description below so people can find them easily. I'll put them on the screen right now as well. So definitely, like if you're interested in quantum, please go to IBM, check it out, start your learning journey. Highly recommend that. The second topical issue I wanted to bring up was something that Jensen Huang said, who the CEO of NVIDIA, just a couple of weeks ago about the timelines of quantum computing. Now, obviously, he's very deeply invested in a certain type of computing, so it probably suits him that it might be far off or maybe not. So, Jerry, I wanted to like get your thoughts on his take. Maybe you could just restate exactly what his thoughts are, and then like, is he wrong? Is he right? Is he somewhere in between?
I mean, it's hard for me to read exactly what was in his mind when he said it, right? And from my point of view, um, certainly, yeah, it's sort of convenient to talk about it when you're trying to push the GPUs as the be all and end all, right? But from from certainly from the perspective of IBM, we want to put our money where our mouth is, and in terms of like delivering value, right? We're trying to show a roadmap, right, uh, um, where we can really bring that type of user value, at scale. And we have a multi-year roadmap that we've been hitting year after year in terms of scaling the technology, right, at a very core fundamental level of the quantum processor, building all the way up towards the abstraction layers in terms of the usability, right, of the software layer and building into Qiskit. And we certainly have targeted within this decade the delivery of a fault-tolerant quantum computer, right, with Starling to users in 2029, right, and then a even larger fault-tolerant machine by 2033, Blue Jay, right. So we certainly see this as our roadmap and how we feel that we will be, bringing that type of differentiating value, right, for quantum computers. Um, Not to replace, GPUs, not to replace
Right.
the traditional computers today, but to augment that and to work alongside that.
And where can people find that roadmap, that timeline that IBM has put out?
Oh yeah, I mean we can share that. That could be a graphic we could share with you to flash up too. I mean that
Absolutely. All right,
yeah,
I'll put it
yeah,
on the
yeah,
screen as
yeah,
you're talking about it, and then
yeah,
also I'll drop a link to it in the description
yep.
below as well. All right, Jerry. Last question for you. I know you're very busy, so we have a few minutes left. I'm super curious how you got into quantum. What was that first moment where you kind of fell in love with it and you knew you wanted to spend the rest of your life looking into this incredible technology?
Yeah, I mean that's certainly my personal journey. Uh, I've been into math and science for as long as I could walk, and part of that was I grew up in a household that was very science and math oriented. My father's a retired physics professor. He worked in nuclear physics for many years, and so always instilled in me this learning, right, of math and science. And from the point of view of quantum, though, I think that I really got into it more when I went to college. I actually was exploring like what are things that I could get my hands on and actually do some kind of experimental work with, right? But that was also um, challenging and maybe a little esoteric, right? And so yeah, I was reading various articles about I think at the time it was about quantum dots and I went and found a professor at Harvard at the time to like talk to him about it, and I went and asked if I could work in his lab. And then when I got into his lab, I started working on actually pushing little carbon nanotubes around. That was I think my first experiment of what I was doing in the quantum realm, far away from actually building qubits, right? But it was working with something that was at this nanometer scale, right? But trying to study things like electronic transport properties. And something like that just, resonated with me in terms of, wow, we can work with things at that scale. And then later on, that got me, learning more about the quantum realm and how to build qubits, and eventually led me towards the superconducting architecture that I went on to do in my PhD.
Awesome. Well, Jerry, thank you so much for your time today. If people want to follow you directly, what's the best place? Do you have an X account that you want to share?
My X account is JM Chow. You can also follow me on LinkedIn, right? So I have a number of updates that we often share on LinkedIn.
Okay. And then for IBM Quantum, where's the best place to learn more?
Yeah, I think, the best place to find out more about IBM is certainly at our website, ibm.com/quantum, to learn
Awesome.
about, our offerings, our systems, our software stack, and everything.
Jerry, thank you so much once again. This has been fascinating. I'm hoping to cover quantum more on this channel. Would love to have you back anytime you have some free time again. Thank you again.
It's my pleasure. Thank you for having me.